China just built train faster than commercial airplane, 1,000 kilometers per hour, on ground, not in sky. This changes everything. The physics problem. For over a century, trains bound by fundamental physical constraints, steel wheels grinding against steel rails, creating friction limiting speed, air resistance increasing exponentially with velocity. These immutable laws of physics defined maximum achievable speeds. Until now, China developed train that doesn't just push these boundaries, eliminates them entirely, removing physical contact with tracks, dramatically reducing air resistance through vacuum tube technology. Result, machine traveling 1,000 kilometers per hour, faster than commercial aircraft cruising altitude. Boeing 737 cruises at approximately 885 kilometers per hour. This isn't incremental improvement. Complete reimagining of what ground transportation can achieve. Fundamental issue: friction. Every time steel wheels contact steel rails, energy converts to heat and noise rather than forward motion. At 400 plus kilometers per hour, friction generates enormous forces wearing down both wheels and tracks rapidly, requiring constant maintenance. Engineers minimized friction through precision manufacturing and specialized materials, but cannot eliminate it entirely. Wheels must touch rails or train cannot move. Conventional speed ceiling. Consider China's CR380A. Reaches 420 kilometers per hour in testing. Impressive speed requiring years of engineering refinement. Aerodynamic nose inspired by fighter jet design. Cuts through air resistance like blade through water. Demonstrates remarkable endurance, maintaining over 350 kilometers per hour for hundreds of kilometers without mechanical degradation. Advanced cooling systems using specialized fluids prevent engines from overheating during extended maximum power operation. Receives electrical supply continuously while moving, eliminating technical stops during long journeys. Yet despite these innovations, CR380A effectively reached practical speed limit for conventional wheeled trains. Japan's Shinkansen E5 exemplifies perfection of conventional rail technology, reaching 320 kilometers per hour commercially. True achievement lies in reliability rather than raw speed. Average delay across entire Shinkansen network, merely 18 seconds per year. Nearly impossible punctuality given modern rail system complexity. Each component functions with Swiss watch precision. Artificial intelligence detects and prevents problems before they occur. Maintenance so meticulous parts replaced before showing slightest wear. Shinkansen's 60-year operation without single fatal accident represents safety pinnacle for conventional high-speed rail. Yet even this masterpiece of engineering cannot escape fundamental physics. At speeds above 350 kilometers per hour, wheel-rail friction becomes increasingly problematic. Solution requires abandoning wheels entirely. The air resistance wall. Even if friction could be eliminated, another barrier emerges: atmospheric drag. Italy's Italo-AG demonstrates sophisticated approaches to this challenge, reaching 360 kilometers per hour through intelligent aerodynamic design. Unlike traditional trains with locomotives concentrated at front, Italo distributes power throughout entire length, allowing quicker acceleration and better space utilization. Ultra-lightweight materials reduce total mass, translating to lower energy consumption and higher speeds. Advanced suspension eliminates vibrations even at maximum velocity. Yet despite these innovations, air resistance remains insurmountable. At 400 kilometers per hour, approximately 80% of train's energy fights atmospheric drag rather than propelling passengers forward. To achieve truly revolutionary speeds, engineers needed eliminating not just friction, but air itself. Magnetic levitation breakthrough. Solution to friction emerged through magnetic levitation technology. Instead of wheels contacting rails, powerful magnets lift train completely above specially engineered guideways. China's electromagnetic suspension system, train floats just millimeters above tracks, held by electromagnets controlled in real time through advanced electronics. No wheels means no rolling friction. Only air resistance remains. This tiny gap, often less than 10 millimeters, maintained through constant magnetic force adjustments. Responding to thousands of calculations every second, EMS technology relies on magnets positioned both above and below train's guideway. By carefully tuning attraction and repulsion between magnets and coils embedded in tracks, engineers lift and stabilize trains weighing dozens of tons. System sensors and control units monitor gap at microsecond intervals, making corrections keeping trains perfectly balanced even during acceleration beyond 600 kilometers per hour. Japan's L0 series Maglev demonstrates this technology's potential, having reached 603 kilometers per hour, currently world record for magnetic levitation trains. Though not yet commercially operational, scheduled to enter service 2027, transforming travel between Tokyo and Osaka. Journey currently taking 2 hours 15 minutes on fastest Shinkansen, reduced to just 67 minutes. Uses superconducting magnetic levitation, maintaining 10-centimeter gap above guideways without touching anything. Suspension system maintains perfect stability even at speeds exceeding 600 kilometers per hour. By floating completely, eliminates friction and wear, allowing velocities no wheeled train could safely achieve. Yet even at 600 kilometers per hour, atmospheric drag remains limiting factor. The vacuum tube revolution. China's engineers recognized magnetic levitation solved only half problem. To reach truly extraordinary speeds, needed eliminating air resistance as well. Solution: place Maglev trains inside tubes where air pressure dramatically reduced. Principle mirrors what allows spacecraft to travel at extreme velocities. Without air creating drag, acceleration can continue to far higher speeds. T-Flight Maglev operates inside these low-pressure tubes, combining magnetic levitation's frictionless motion with vacuum conditions that eliminate atmospheric drag. Result unprecedented, speeds reaching 1,000 kilometers per hour, surpassing cruising speed of Boeing 737 aircraft, which typically fly at approximately 885 kilometers per hour. Achievement represents culmination of decades spent understanding and overcoming physical barriers that limited conventional rail. Practical implications transformative. System could theoretically cover distance between Beijing and Shanghai in less than 2 hours. Journey currently requiring 4.5 hours on world's fastest conventional high-speed trains. Ground transportation suddenly becomes competitive with aviation for distances up to 1,000 kilometers, fundamentally redefining intercity travel possibilities. Engineering the impossible. Achieving these speeds required solving problems far beyond those facing conventional rail designers. To reach extraordinary velocities, every gram counts. Chinese engineers turned to carbon fiber bodies and lightweight superconducting magnets, reducing train mass while maximizing magnetic field strength. Carbon fiber shells flex within safe limits while remaining rigid enough to maintain structural integrity. At speeds where atmospheric pressure differences become significant forces. Japan's experimental Shinkansen Alpha X demonstrates similar weight reduction principles through different technology. This 10-car, 320-meter machine reaches 400 kilometers per hour in tests, employing monitoring systems analyzing more than 10,000 different data points while traveling. Most striking feature, extremely long 22-meter nose designed like spear tip to pierce through air without resistance. Revolutionary, can adjust configuration while moving. Sensors across surface detect strong winds or pressure changes. Automatically adjust position to maintain extreme speeds without losing stability. Emergency braking system can completely stop train from 400 kilometers per hour in just 2 minutes, surpassing all world safety standards. Though designed for conventional tracks, Alpha X's innovations inform vacuum tube maglev development. The breakthrough test. Engineers gathered in control room, eyes fixed on monitors. Prototype maglev built with carbon fiber shell and loaded with sensors weighted at track's far end. Lead engineer Dr. Liu from Southwest Jiao Tong University recalls tension before run. Previous month, resonance issue forced emergency shutdown at 590 kilometers per hour. After weeks recalibrating coil arrays and refining active damping systems, team prepared pushing beyond 600. Train accelerated with low steady hum, gliding above guideway on magnetic cushion. Within seconds, digital speed readout climbed past 600 kilometers per hour. Data streams showed vibration levels holding steady, carbon fiber body flexing within safe limits. In control room, technicians shouted as counter ticked past 605, then 610. Run ended with smooth deceleration. All telemetry in green. Test confirmed combination of magnetic levitation and reduced atmospheric pressure could achieve what conventional technology never could. Speeds genuinely competitive with aviation. The passenger experience. Journey between Beijing and Shanghai by vacuum tube Maglev promises experiences fundamentally different from both conventional rail and flying. Instead of long drives to airports and security lines, passengers board in city hearts. Train glides from stations, accelerating with gentle pushes. No jolts, no sudden climbs reminiscent of aircraft takeoff. At full speed, rides almost silent with barely hints of vibration beneath seats. For trips under 1,000 kilometers, city-to-city connections erase hidden hours spent on ground transfers and boarding procedures. On Tokyo to Osaka corridors, studies show Maglev's door-to-door time can rival or beat fastest planes. Thanks to direct downtown access. Comfort inside matches speed outside. Steady pressure, no turbulence. Smoothness that turns high velocity into afterthought. Environmental transformation. Measured by carbon output, differences between Maglev and air travel striking. On current test runs, China's Maglev trains generate estimated 10 to 25 grams of CO2 per passenger kilometer. Figures reflecting both electric propulsion efficiency and country's evolving energy grid. In contrast, short-haul jets on routes like Beijing to Shanghai typically emit between 90 and 130 grams per passenger kilometer. These numbers depend on factors like train occupancy and renewable versus fossil fuel grid mix. But even under conservative assumptions, Maglev's footprint is a fraction of aviation's. Environmental analysts point out that as China's grid shifts toward more renewables, emissions gap will only widen, offering concrete bases for comparing climate impacts of future transport networks. For nations committed to reducing transportation emissions while maintaining high-speed connectivity, Maglev represents a viable alternative to expanding short-haul aviation. The challenges remaining. Vacuum tube Maglev promises speeds once reserved for science fiction, but engineering reality far more complex than test track demonstrations suggest. Building and maintaining near-vacuum tunnels hundreds of kilometers long demands unprecedented precision. Each segment, often 6 meters in diameter, must align within millimeters to prevent leaks compromising entire systems. Energy required to sustain low-pressure environments and keep superconducting magnets cold adds layers of cost and complexity. Land acquisition along busy corridors sparked disputes with local governments and property owners, raising questions about social and financial feasibility. Safety certification for passenger travel at 1,000 kilometers per hour remains undefined. No published protocols for emergencies or rapid decompression inside sealed tubes. These aren't insurmountable obstacles, but they explain why vacuum tube Maglev hasn't immediately replaced conventional high-speed rail. Technology works in controlled test conditions. Scaling it to national networks serving millions of passengers requires solving engineering, regulatory, and economic challenges that will take years to address fully. 2021, China's Maglev prototypes surpassed 600 kilometers per hour on Qingdao and Chengdu test tracks, marking new chapters in high-speed ground transport. Engineers achieved this by combining electromagnetic suspension with lightweight carbon fiber bodies and superconducting magnets, reducing friction and drag to near zero. While public records confirm test speeds above 600 kilometers per hour, claims of 1,000 kilometers per hour remain limited to controlled laboratory conditions. No independent verification of sustained passenger carrying capability. Journey to this point illuminated why conventional technology reached its limits. Trains like CR380A, Shinkansen E5, and Italo AG represent perfection of wheeled rail. Fast, reliable, Efficient within constraints of steel-on-steel contact and atmospheric drag, but to exceed those constraints required abandoning wheels entirely through magnetic levitation. Then, eliminating air resistance through vacuum tube technology. What is clear? China's Maglev program stands at forefront of engineering ambition, setting new benchmarks for speed and sustainability in transportation. Question no longer whether these trains will replace airplanes for medium distances, but how quickly it will happen, and whether rest of world will keep pace with Chinese innovation. Which aspect impressed you most? Elimination of friction through magnetic levitation? Vacuum tube solution to air resistance? Engineering precision required to maintain stability at 1,000 kilometers per hour? Would you travel at such speeds on land? Share thoughts in comments. Subscribe for more coverage of transportation innovations reshaping how humanity moves across planet. Thanks for watching. See you in next one.